Well, all right, so this is the last section for Unit 2. We're going to call it radioactivity. So this is 2.4 radioactivity, and we're going to look actually on the inside of the atom. We're going to look really down deep into the center, in the nucleus of the atom for this unit. So let's get a couple of terms out of the way first. Radioactivity is just simply the process by which nuclei give off particles and rays. When we talk about radiation, we're talking about those specific rays and particles that have been given off. So radioactivity, that's the process by which the particles are given off, and radiation is those particles and those rays themselves. If something's a radioisotope, that just means that it's an unstable isotope of an element. So carbon-14, like we talked about in class, is a radioisotope because it's unstable. Carbon-12, on the other hand, which makes up the most of the carbon in your body, that's a stable isotope, so that would not be a radioisotope. So what's actually happening in radioactivity? Well, unstable nuclei want to be stable. They want to be completely stable, and so in order to become stable, they have to eject certain particles and certain energies to become stable in the nucleus. They undergo major changes in order to do this. Some of them actually change the identity of the atom. Uranium, for example. Uranium's radioactive if it's got a certain atomic mass, and as it decays, as it spits out particles and energy, it actually becomes a new element. And it continues to do this. It passes through promethium, and it passes through radon, and passes through all these different types of elements until it settles on lead eventually. So, yet uranium, if it's radioactive, it will eventually turn into lead, which is a completely different element. As these changes occur, radiation is given off. And there's different types of radiation. Some is really, really bad for you, like you wouldn't want to be next to some radioactive uranium that we use in the nuclear plants. You wouldn't want to stand next to that too long. Some of it is not harmful to you whatsoever. We actually use them in medical processes to investigate certain things that are going on inside of your body. So how do we measure radioactivity? Well, we use something called a half-life. A half-life is just defined as the time required for 1/2 of the nuclei of a radioisotope sample to decay. So essentially it's like saying, how long is it going to take for 100 grams of this stuff to go down to 50 grams of this stuff? The faster that is, the faster that goes, the shorter the half-life. And sometimes that means the more radioactive that substance is. So putting that in layman's terms, this simply means that after every half-life, half of the sample will remain, and half will have changed into a more stable isotope. We can take a look at a decay curve, and we're going to make these, or we have made these in our lab. This is a decay curve for the specific radioisotope of carbon-14. So we talked about carbon-14 being present in our bodies and then actually decreasing as we pass away. Let's say it starts at 100 grams. It's going to take 50 years for that sample, it's going to take 5,730 years for that sample to actually decay down to half of its original value. So we started with 100 grams. It's going to take 5,730 years for it to decay down to 50 grams. It's going to take another 5,730 years to decay down to 25 grams. And that process is going to happen over and over and over again. Now, if you do this, if you think about this, will that sample ever reach zero? Well, if you continually cut something in half over and over and over again, it'll actually never reach zero. We can have a mathematical equation that'll help us define half-life. And this is the equation that we should kind of stick with in class. It's 1/2 raised to the nth power equals the percent substance remaining. And in this equation, n is just simply going to equal the number of half-lives. So we can use this equation to solve some problems that we might ask in class. We're going to take a look at 2 of those in this PowerPoint. So let's say you start with a 36 gram sample of radioactive thorium that has gone through 3 half-lives. We don't know how much thorium remains. Now there's 2 ways to go about this. I'm going to use that equation on the previous page to go through one way. So let's say, okay, 1/2, we said that's going to be raised to the nth power, so in this case that's 3, okay, and that's going to equal the percent remaining. Okay, so 1/2 raised to the 3rd power, let's see, that is going to be a total of 0.0 0.125. Now notice that's 12.5%, just written as an abundance right here. So if we had a 36 gram original, 36 gram original, we would just multiply that by 0.125. And that's going to give us a total new mass of 4.5 grams. So if thorium goes through 3 half-lives, we are only going to have 4.5 grams of thorium remaining. So that's one way of going about a problem like this. Another way, and in this way you may have tried to figure out on your own, is to say, okay, it's 3 half-lives. That means that I have to cut the original number in half a total of 3 times. So that would be, let's see, 36 divided by 2. Well, that's going to equal 18. Let's divide that by 2. That's going to equal 9. Let's divide that by 2. That's going to equal 4.5. And if we count that up, let's see, we did 1, 2, we did it 3 total times, and so boom, there it is. There's my final number again. That's 4.5 grams at the end of the day. So both of those ways work. The equation way, the way that I showed first, is going to be, let's see, a little bit more universal, because at times, this number right here, the total number of half-lives won't be a whole number. Like, so for instance, I might give you, it goes through 3.6 half-lives. And then you'd have to use the equation to figure out how much is going to remain. Let's go to one different example. And this example is going to look at radon. So the half-life of radon, we're going to say, is 3.8 days. We want to know how many days are required for 5.23 grams to remain if you started with 105.4. Well, by giving you these two values, we can actually figure out the percent remaining. So what we'll do here is we'll take 5.23, the mass that remains, and divide that by the original mass. And when you do that, 5.23 divided by 105.4, you get a relatively small number. It's about let's see, it's 0.0, the stylus isn't working out so well, 0.0496. And so now your equation looks like this. It's 1/2 to the nth power equals 0.0496. All right, now we have to use something called a log to get that n all by itself. And we're going to log both sides of our equation, and the button is on your calculator. It's just simply pushing a button. It's getting rid of an exponent. And so it looks like this. We're going to take n log of 0.5, because 0.5 is equal to 1/2. And what you do to one side, you got to do the other side. So you're going to have a log of 0.0496. That's a 0 right there. Okay? So you'll notice the n comes down and it goes in front of the log, and then comes the 0.5 or the 1/2. Now if you solve for n here, you use that log button on your calculator. N in this case is going to come out to 4.33. And so we got to remember what that means. That is going to be the total number of half-lives. Okay? That's the total number of half-lives. Well, what's 1 half-life? 1 half-life is 3.8 days. 2 half-lives would be twice that. 3 half-lives would be 3 times that. 4 half-lives would be 4 times that. 4.33 half-lives would be 4.33 times that. So to get our final answer, we're just going to take our 4.33 times 3.8. And our value here, 16.5. And if we think about, okay, what were we solving for again? It's always important. It's going to be how long, okay, how many days are required for 5.23 grams to remain? Well, it's going to be about 16.5 days in order for us to reduce the sample down to that size. Okay, that's radioactivity.